Welcome back to the second part of Lecture 3, Apache Spark for Cloud Applications. In the first part, we reviewed really the basic capabilities of Apache Spark, which was RDDs, it was about head nodes, about worker nodes, and the scalability that really is existing in Apache Spark to scale up with a number of worker nodes nicely to your problems. So this was really more the hardware view on it. So you have, of course, hardware. You can scale up and having a software framework that is able to scale up and down. Of course, you have to pay the price for it when it comes to hardware. That means if you want to leverage the benefits of Apache Spark in memory, which we thought is a very good idea compared over Hadoop, then you have to pay the price for it. Memory intensive systems or everything which has lots of memory is of course extremely costly. Hence, we will find still startups, smaller companies which haven't so much budget, still operating a lot of stuff on Hadoop, right? Because essentially it's slower, but it does the same thing. There are machine learning libraries like Mahout, while we learned today something about more MLlib, which is the Apache Spark version. But still think about this is of course related to costs. And what we now want to look a little bit into the second part of the lecture is the ecosystem around Apache Spark. So we learned the basics in memory is important. We have seen that the RDDs are nicely parallelized just by a couple of Python lines really in your Jupyter notebook, maybe using PySpark and a couple of lines, a filter, where we have then implemented shortly word count, which was really just one slide essentially, but then one line essentially. And this is remarkable if you think about former days about parallelization, synchronization of the input of the output, temporary data, putting it somewhere. All of this had to be programmed by yourself. So the takeaway message of lecture 1 is really Apache Spark and Hadoop give you lots of tools at hand to abstract from all of these difficulties in parallelization and make it much more simpler for you to approach it. And of course, to make it even simpler, they have lots of libraries which leverage this kind of simple functionality. So you find different Apache Spark libraries on top of the core, or what you see here, the blue Apache Spark, which should represent the core on the left here, bottom. You will find 4 interesting libraries which are there in Apache Spark and quite powerful, which is Spark SQL, structured query language. We'll talk each of them. We will have some, example for each of them. And there's Spark streaming, there's machine learning library on top of it, and also the graph, which is quite interesting when we do also one example. Now, when we also look on this on a broader perspective, of course, this is not something which is just, let's say, Spark. So there are different tools in this ecosystem. And if you look in the open source community, you will find so many different tools which have one from another derived the MapReduce model for different specific purposes, for streaming, for interactivity, for workflows. You have Pregel, for instance, you have Storm, you have streaming support. And this is all interesting when you look on them. And of course, because it's so nicely integrated into Spark, you see here in this graph that the performance usually is quite nice by having Spark underneath it. And this is also, again, because these are all different open source projects in the past. And now, of course, you have a kind of very fundamental good base with, using in memory, of having a really fault-tolerant, resilient data set or distributed data set, really, so the parallelization is there. So with this, you really can build on top and have a very nice performance when you think about the different problems that you have. And as we understood now, essentially, I have always, in one way or another, this kind of 4. And as we understood from our logistic regression assignment and also the lecture, they all go together partly, right? You use Spark SQL together with the machine learning library, or you have a GraphX problem, the graph library, and you do some machine learning with it. You use streaming and you filter, and the filter is then put to some machine learning model. So of course, this is not exclusively, as you know from the Jupyter notebook we have explored the last time, you can actually import this quite neat with PySpark again in your Jupyter notebook and use them, of course, in parallel. And this makes it, of course, very nice also when you think about it, that it's a very nice library setup on top. of a very fundamental core, which makes it, of course, very fast again, and not only compared to Hadoop, but also to the specific products which are on the market, maybe just solving specific problems like SQL, graph, or streaming. One of the examples which is quite, let's say, important for big data is, of course, data which is in traditional relational databases where you use a JDBC, for instance, to connect to, or you have other forms of, let's say, more structured data sets in a comma-separated value or JSON file. So there are basically different data structures around in a data frame and data source API that nicely abstracts from this, so that you can essentially program in this Python like you would do it with a relational database in SQL, and it would encapsulate this through all the different layers. And this is, of course, very nice for a specific type of data. As I said, it must be mostly somehow in the form of structured data. Otherwise, you probably would have necessarily a SQL access. Nowadays, there are also new document-oriented databases, NoSQL databases, key value stores, which are getting more popular. And we have those in subsequent lectures. Just take away the message that many, or really very much, of the data that you have today is still in relational databases in companies, right? So traditionally, when it's about customer data, for instance, people move very slowly. They have an established database, they accumulated data, maybe in an Oracle database over many, many different versions. And now they're hesitating of just switching, tomorrow to another database because it has stands the test of time. They have a support contract with, let's say, for an example, Oracle, can be other database providers, but Oracle is very prominent. So you have to still think about that you want to do machine learning and you want to use Apache Spark, but you want to access this somehow. So for this kind of Spark SQL is just very nicely. And you see the performance again here with Hadoop, of course, is quite nicely, because here you have kind of a native support for SQL. You don't drop first the SQL statements and the results from it to disk and load it again per iteration. Here you again have it directly in a so-called Hive context, which is a specific, let's say, open tool again, sitting, very closely to Apache Spark, is having an almost SQL-like language, right? Of course, it's a little bit different because it's more tightly integrated, but that makes it easy to have it, let's say, in things like a Jupyter Notebook. And we use this already indirectly without you knowing in our food inspection example. By now, I think many of you have started the assignment. That's, at least I hope. Don't wait for the last minute before you have to submit. So here you see that we imported the PySpark SQL aspects, and we did the data frame where we show here that is nicely structured data, right? We have IDs for every different name of the restaurant. We have something about the, kind of inspection, if it failed or passed, and the violations we wanted to learn from. This is just 5 rows, but of course, very structured. For this, SQL makes just sense to work with it. And then we have a nice data frame really in Apache to play around with it. As I said earlier, data frame, pandas, this will be a topic we explore a little bit on Thursday. I didn't want to overload you putting this also here. We will put new elements of how to work with data structures on Thursday in the practical session. But this is traditional, really, Spark, as it was also in, let's say, the subsequent version, the previous versions. Now, the next kind of library, which is very important, it becomes more and more important, is streaming library. The point is that data gets more and more. It's getting big data. We have seen in the example of the square kilometer array with 1 petabyte every 20 seconds, that the data and the sensors getting so fancy that it's impossible to keep all the data, perhaps in the future. So what we have to do is to look inside the stream. Also, when you think about a Twitter tweet now, about your product, about your company, bad media, about your startup, and you want to counter this, and but in a startup, you have just 2 people sitting there. So you cannot have one doing social media all the time and looking over all what is said. So here you have maybe a util that you can use in the streaming and just do everything, filter it, as you see there, contains Spark. You can also put filter contains your product of the startup, and then you basically have a sliding window, go through all the Twitter tweets. And then, have a much more faster report, probably, what's, told about your product. And this is, of course, an interesting thing because you're not really interested in the tweets now that have been maybe done, in the last year or so, because now it's time to market. So you want to respond quickly to bad comments and counter-react and say it's not the case, and etc. Also think about it, it appears all as a stream, but all of you know that there's no 100% in computer science. So that means things will fail. A node will crash. For instance, we will see in lecture 4 very soon, when we have the real data center design, that hardware always fails in this large data centers particularly. So which means there would be a node crash. So the software is not there. So you can basically expect failure by default. And this is also what these kind of libraries bring you. That means even if you have here now high velocity, Spark is prepared to restart or reshift this task that you had for the stream to another node that is still existing without starting from scratch, because then the data might be gone. You don't want to keep it. This is essentially another interesting aspect where it makes sense to combine the streaming with Apache Spark and this fault tolerance. It's really about time. Of course, admittedly, there needs to be a specific application for it, right? Like Twitter, social media in general has a very high frequency to react, but also to view. So here it makes sense, as you see there in the Twitter utils, for instance. However, note that the Twitter API, of course, you don't get all the data. You have to get Firehorse or so, which then, of course, costs something to get to all the tweets. But still, it's one application example that you can really look into. I think I'll leave this for now. Streams are incredibly interesting. There are new tools around, new Apache projects, but this will come in lecture 15. So we will postpone a little bit about streaming and we'll focus more on other interesting libraries that we have. Like, for instance, here you see a good example of essentially having the machine learning library, which is a large fraction we already have used with logistic regression. Let me start here the video. Where you have then also lots of other algorithms. Of course, logistic regression was a classification of data, very specific problem. We learned it was a binary classification problem, so not very strong in terms of classifier or in terms of a machine learning model. Then we learned in one of the lectures that classification is only one big bunch of machine learning techniques. So this library also offers solutions for clustering. And one of the clustering algorithms you see here, which is admittedly a very simple one called k-means, will basically assign, as you see in the video here on this slide, the black dots, which are, essentially without any class, without any cluster, and will assign them to specific clusters. And this is done on, Euclidean distance, as you see, the nearest points to this so-called centroid here, that is these kind of colors that always move. They essentially will be, initialized very rudimentary. And this number of k means how many of those you would have. So nobody guarantees you also that you would have, let's say, 4. You can also do 3. Then you maybe end up with 3 clusters, and that look maybe much better. So this is, of course, also a problem of this algorithm. You don't know exactly how much clusters you may have. So you need to do some data inspection to really think that it's about 4 clusters. But you nicely see in this example, for instance, you initialized all on the top right, but they will move automatically given the algorithm in a parallel fashion implemented in Apache Spark to a basically area where the error of the kind of different Euclidean distances to each other, where the clusters are get, more or less good defined by the points. And this is really iteration. So iteration, and the k-means algorithm is, a very simple one, but you see here on the right-hand side, it's already there with a machine learning library. So essentially you have a kind of couple of points you want to parse, and then you train, and the only thing you have to worry about is really a factor k, which is then the amount of clusters you want to have. And this is, of course, a large area in machine learning, and there are different clustering algorithms on the market. Just shows you that machine learning library has lots of these different ones to offer. And we look in Practical Lecture 3.1 on Thursday much more into some of those, just to give you an overview what basically is there, and to understand logistic regression a little bit more that you already used the last time. But again, Practical Lecture 3.1 will not only do a few demos for you to understand how it works in the cloud on Thursday, also to look much more on what is this stochastic gradient descent and what is the optimization in it. Because one of the elements in machine learning is that it's not always so simple like the perceptron learning algorithm. So there it was adding a vector, subtracting a vector, adding a vector, subtracting. Boring. Over many, many iterations, you converge to zero error. This zero error was essentially just possible because it was linear separable data, which is not the case usually. You would always have some error. There's a, let's say, one dot, one point that is misclassified somewhere in deep far, a green one in the red region, noise in the data. So usually you have this knot. And basically, logistic regression deals with this, but also don't have just the perceptron learning algorithm. It has another learning algorithm, so to speak. The learning in this sense means reducing the error. And if you look on the bottom left, we discussed this the last time. Instead of taking the sign that we did for the perceptron learning algorithm and then -1 + 1, adding it to the PLA, we said, let's put it to a sigmoid function. It's still this dot product, so kind of the linear sum, using weights, but then you put it to the sigmoid or to the logistic function, which is, 1/1 + e to the minus whatever the signal is. In our case, this t is, of course, here this w transpose x, or basically the dot product of both, which means when you put it in a Jupyter notebook, it looks like this a little bit, which is then really this logistic function or the sigmoid. So you have still the signal you basically put in, you have your x, and then it will basically look and squash every little one between 0 and 1, right? And this gives you then an interesting way of computing the class, of saying, is it either 1 or 0? But think about it that you always have also this y, right? So where you said we have this guiding y label that can tell us something about it, where we can compare, which is here in the loss function. So the loss function would have, this w transpose x, it have the label y, and will tell us a little bit how good we are. Here's a logistic loss, a loss function that is used in machine learning. And in order to get the error down in this, because we have to learn, we always do, some form of an optimization. You can look at now in two directions. One is that you want to have the area under the curve, the error curve here, larger. So you maximize this, of course. And then what we do, we turn this maximization basically into a minimization problem of saying we want to have always the lowest error basically possible. And we go really with the stochastic gradient descent, so to speak, from a function like the error function downhill. And like in the mountain, going lower and lower with the error, we basically take then, as you see here, the negative gradient. So to really move step by step downhill to find the lowest error. This might be not 0, right? This is an important part. Usually in machine learning, you have it very rarely that there's 0 error. And if so, you should be very, question yourself if that's a good model, because it really seriously sounds like overfitting. So, but these are, let's say, also alluding to many more elaborate machine learning topics like overfitting, underfitting, lack of generalization and things like that. But also Practical Lecture 3.1 give you a bit more view into this. And also in subsequent lecture, lecture 6, we will come back to things like gradient descent, because this is an optimization, let's say an optimizer, which is used in many different machine learning models. So it's not only here in logistic regression, for instance, it's an optimizer that stands on its own. And we as machine learners, we just take it as a tool to different algorithms, for instance, like machine learning. Or deep learning, or whatever model that comes around. So this shows you a little bit how that worked. So instead of having just the perceptron learning algorithm, under the hood, Spark is executing the stochastic gradient descent. We will learn a little bit more how this is exactly done. But of course, it is really trying to get this W, the weights, let's say, less and less error prone so that you have a model that comes better and better in terms of performance. So by minimizing the error, you're of course going towards a better, let's say, accuracy or score. What you see a little bit here with the area under the curve. Of course, here it really alludes to, if you want to do very deep details on this, you need to do a machine learning course. We cannot cover all of this because we also do parallel computing, cloud computing, big data. But here now you have the basic simple ideas already to connect to many different lectures in machine learning. And in terms of performance, you really see that, interestingly enough, again, Spark points. And why it is pointing? It's because of the iterations to learn. That's why Spark is here so much faster, because you have to think about it, that what it means. We touch the data not once, we touch the data again. Compared to the error, compared to the real labels, we see the error, we want to downgrade the error, we change the weights. Let's have another iteration. Okay, compared to the outcome, is it this or that class? Oh, there's an error. Change the weight. So long story short, we go iteration, and try to knock the error down by using the stochastic gradient descent again and again and again after iterations. And because of this, we are much more faster of having this done in memory. We don't need to reload data from HDFS, for instance, right? It means in k-means clustering the same way. If you have basically always Euclidean distance between the different points, but you have to have the points always on HDFS, you load them again, you have to compute them, you have your centroid, you drop it to disk, then you load it again. So Spark keeps that in memory most of the time, especially for smaller problems. And then, of course, the time per iteration is, so to speak, very, very fast. And with this, the solution is also much more faster than Spark. And through this iterative nature that machine learning has, this is, of course, a very beautiful part, not only to make it partly parallel, right? So this is an important part of it, but also actually to make it faster in terms of reusing data which is already used before. The data, in a sense, the x's, if you remember, will not change, right? The data itself stays where we learn from. The only thing we change again and again are the w's and the weights. And this is, of course, an important part. And with this, you have numerous benefits in using memory to the maximum extent. Now, when you look about the selected algorithms that are there, and there's a growing number of algorithms, classification algorithms from logistic regression to naive based, several regression algorithms, not only linear regression, survival regression, support vector regression I have seen also. So there's different models that you can use. All of them, let's say, are really more in the domain of traditional machine learning. If you now think about deep learning network, convolutional network, long-term memory, GANs, and whatever, you don't want to really use a machine learning library here. You go to TensorFlow, you go to Keras, things we will cover in lecture 6 and 7, things like PyTorch. But of course, here you see still tree-based approaches are still stand the test of time. They are still used. Of course, decision trees usually overfit a lot. So people use random forests. They don't grow one classification tree. They sort of grow 1,000 of decision trees. That makes it a random forest. And then you have several boosting and bagging strategies. But it all would be going too far to explore all of this in this part of the lecture. Then another strong field where really this machine learning library is quite interesting, in my opinion. There are other ones from Scikit, and there's other, on top libraries in Python that you will find. But here, the Alternating Least Squares recommendation engine for movie rental that we will explore is a relatively easy way of getting a recommendation engine going. So if you're a startup, you don't have money for large customer relationship management that have that included, or database analytics systems which come, in commercial spaces, you relatively quick can here start of having, recommendation engine your own. You just turn the movie example or other examples you have into your kind of startup idea or product, and customer likes or references, whatever it is you have. Ratings is a very important word in this regard. Do we have a 1-star rating for a product or a 5-star rating? The beauty is it is also personalized, right? Collaborative filtering techniques But again, we will cover this in practical lecture 3.1. So let's not take away all the material we actually put in that lecture. And it's actually also better understood if we go to with some practical, examples alongside it. Then there's a huge area of, pattern mining, frequent item sets, association rule mining. We have an expert here on the call, Shadi Barakat, one of my PhD students, who, for instance, does this a lot already. Also, Spark offers here something that is all about shopping, data analysis. This person that buy this will also buy that. Or these are shopping baskets, usually together. So the nice thing is that's usually not just a dual, so it's just not, product A is bought when product B is bought. The beauty is here in these algorithms that you have a triple, for instance. So only if these two bought together, then the third one is bought. Things like this, where the human mind usually stops, because otherwise you go to a shop and they will say, well, I knew this since many years, right? These duals are kind of known. Beer goes with diapers. I will reveal the reason why in one of the lectures that we have about data mining in the end of the course. But it's still something which is very practical. And this leaves me the opportunity to say it is an open source project, this Apache Spark and the machine learning library. And you see that all the algorithms there are really much driven by having things which work in business, in kind of these areas. When it comes to science, engineering here and there, you would maybe go for other solutions. You maybe even go to deep learning algorithms. But pattern mining, frequent item sets, and so on, there's no point necessarily of using deep learning. You can use deep learning. There are also new methods there, but there's simply not a need. So let's look on the remaining one we have. As I said, more machine learning will really come in the practical lecture. Let's explore what Apache Spark has to offer for another emerging large field in terms of handling big data, especially as you also will notice more and more things. If you want, Canvas, for instance, from the university is also kind of social media aspect. Everything moves to something where we can like everything, where there are connections between different things, there are links between different modules, whatever it is in your product, the same way in customer relationship management, in social media, in social networks like Facebook. You will always see that the structure of the data is getting more and more really extremely unstructured and very much linked, so the friend of the friend. Or you have things like this where you basically have the web. So there's a really undynamic grow of the web, as you know. So there's some web pages that strive, they just have lots of visitors, forums which have lots of people, and some that have, let's say, just like 10 likes or 10 people on board. So you have to have some weights on the different, links to say, if you are a search engine, you want to rank them. And this is another application example I would just here leave on the table for you, a very easy one in a way to show how beautiful, graph databases essentially can work with this. And we will have an example how that works basically here in the couple of slides I will show in this part of the lecture. So think about that Google had that really, of course, as one of the pioneers, and they had this interesting idea of this PageRank, which is now a name which stands on its own, but at that time it was relatively new. And of course, this was at a time where Google was better. Do you remember this? So Google was once better, right? There was Yahoo, all other search engines were quite established. And now Google has lots of services, not only cloud services, but in every almost region of a business, you can find Google. So it's also an interesting thing. This all started more or less with a web search. That's why it's so interesting to think about this, how quick an innovation in computing can really bring something big. The idea was also to have, let's say, websites which are, it's more faulty, or basically websites which are not so much, let's say, real honest websites, but more like spam websites with lots of hidden words and which are not really off or basically representing the topic of the web page and stuff like this. So in a way, there was lots of rubbish and so on, more and more coming on the web. So the question was how you can filter this out, and thinking about that the web is maybe a graph. I think that's something we all can in one way or another understand, but it is not equal, right? It has not the same links to everywhere. Some link heavily on one specific website, And your private personal website maybe not so fancy, so then you have, let's say, just a couple of forums that link to this, while you say the University of Iceland or University Hospital from Iceland, for instance, would have lots of links to it. So of course there's a meaning to this, so we have to understand that when something publishes on this web page, it has a certain meaning than on another web page. And with this, of course, a ranking in the Google search, right? Or on the other more or less searches, because they all, of course, now implement similar mechanisms. So when you look this a little bit more formal, this is something where we have some, let's say, things where we have interesting formula you see here, where you can now really abstract from the web as it is right now, and always think about you have to have kind of the graph as it is represented right now, and you want to do something with the graph. You want to rank the graph to a better way so that the nodes have a certain rank, and the higher rank, the better. So you would basically have something like, when you want to work with it from a computer science perspective, you have the rank before at time t, and you have the kind of next step, t+1, right? So in the next step, what we want to do. I have a very practical example of this. I know it's a little bit theoretical. And of course, think about then that you have also a decay factor in this, usually when you come to a real implementation on this, because you want to do also here and there some randomness catched, and which of course is good to have. It is a more or less a little bit seen, if you want, like a regularization factor. Regularization is a very important topic in machine learning and working with data. Unfortunately, in this lecture here, we cannot talk too much about it, but it says a lot of things how you generalize well. Anyway, I think when we look at this, we see, and there are lots of, let's say, different edit literature material if you really want to know more. Look at this on a more practical idea, right? When we have a concrete example we walk through. And you see here the web that was on the top right in databases, a bit more how it is in our mind, right? They're very popular websites. They're popular forums. They're, let's say, very small websites, but they tend to do, point a lot to the big websites, if you want, all in all. So this is something where now, if you face as a computer scientist or machine learning expert now to think about this, and what would you do, right? How you would rank them, right? You cannot just, in a subject fashion, go there and say, that is a nice website, I like it. So everybody has to like it. So here it's really, you have to go iteratively through the web, go along the lines of this graph. And it has an in and out, right? So pointing to someone means an in, basically for the other, and an out for yourself when you look at the smiley perspective here, right, to bring it closer to you. So this is all, let's say, more graph design really, if you want. So if you want to solve it now, you can nicely do this by passing it again through MapReduce again and again. And by this you can give a different strategy of, how you assign weights, actually thinking about the popularity and the links in. So the links are usually somewhere inside this, so you will know basically, or Google knows which page is linking to which other page, right? They crawl this. And with this, they can basically see now, okay, and create a graph out of this. Of course, it's much bigger than the graph I have here as a trivial example, right? Where we see a little bit what we saw on before, a very popular website, which is on the top. You see here already, 3 are really pointing to it, could be the university website. And all of the others are more, let's say, personal blogs from us or from, let's say, normal people. So in this sense, let's look through it. You would say you have a certain rule where the, kind of page, of course, contributes. And if a very, let's say, successful website or popular website points to another website that might be just a blog, it's still something to say about it if they are doing this. So in this sense, it has some meaning and needs to be in these contributions that you see on the top left. So each of this P kind of rank contributes to the neighbors by the things that going out, right? So by the links out. And you see this rule here. And I just want to start with a simple example here. Rank 1 with 2 neighbors. If you go the next time, you will see, okay, you cut it into half on the right-hand side. So you have 0.5. And you contribute this to this nice fellow here because they have 3 coming in. You have 3 times incoming ones, which would be 1. It's the only outgoing one. It's 0.1, so it's 2 overall. And if you do the math a bit right, you will see that already in the first iteration, it comes out that this will be a very high rank website. And the interesting thing is, of course, iteration in it, right? Machine learning lives from iteration. Analyzing data lives from iteration. So you put the rule not to once, you put the rule again in iterative fashion, and you see that it gets balanced out by more and more aspects to basically a final state where we say it converges to the state. And this would be now essentially the Google ranking. You would put the first page on the top, then the others basically in subsequent rankings. And this shows you also the error, right? Number of iterations. By doing this, and of course also the performance of doing this again, it is of course lots of different million links you have to analyze. So you bring down essentially the error rate by more and more iterations, and then balance out the ranking to a bit more honest possibility by going through all iterations. And this is just a beautiful example. Again, we will come back in the MapReduce lecture when we have Hadoop and Spark again compared, when we know a bit more about MapReduce, that of course, when you have things in memory touching the data again, the links again, it helps to have it in memory, which explains here that of course, again, the performance of Apache Spark is by far superior to Hadoop. And here you see also the number of machines, right? The more workers you basically put to the problem here, which is meant by the number of machines, then of course Apache Spark just scales even more better if you have more machines to it. Just towards the end of the lecture, just give me some pointers to, of course, who they're using Apache Spark for different elements, basically for advertising, a huge market we will come back to in one of the lectures with AdSense and other Google aspects also. We have applications at Conviva, which is basically a streaming video company, and others using it also for video streaming aspect, where Spark Streaming is learned. Basically to learn how to optimize the network in real time. And then, ClearStory is another example where you have really Spark technology of a real-time product to look at your data, clear data, and clean data and stuff like this. You see all over the business is actually existing. And the final slide I would like to leave on the table here for you is also something where people or some students already actually have asked and said, what is Google Colab? Can we use it? Of course you can. You see here an example that Google Colaboratory is essentially free. The Pro version is for $9.99 per month, but still a relatively good price. You get faster GPUs, you have much more longer run times. And of course for Spark, more memory, which means you have much more better runtime if you do the premium or Pro version. However, you can use a free version if you want, right? So it's not something you have to do. But let's say in more and more trainings, this gets very popular, this using Google Colaboratory. And if you see, it's essentially a Jupyter notebook that you know already from MS Azure. You can use PySpark there, just a small installation, then you can use it, and essentially has very similar features. Of course, then this is a Google Cloud. It's not anymore Microsoft, so you can have things like Google Drive very easily put to it, which is quite nice when you think about, do you have data maybe there you want to analyze? So things like this. Very famous, very popular, very nice to use these days. Definitely interesting to have a look. So finally, if you want to have a closer look and want to do this, I looked a little bit around in YouTube and found this one. So if you really want to do the exercises in Google Colab to gain some experience for your job or so, please do so. Here you find a video that relatively nicely explains how you have to install Spark there, although it's also on the website I just showed a little bit. And then you basically have the same Python code. It is a Jupyter integrated notebook, so to speak, in this website of Colaboratory. So it will have more or less the same look and feel if you want. Right, so that's all for the lecture basically today. Here are lots of references. Feel free to look at them. So I would stop here the lecture and go to the questions.